Hey there, this is Chemistry Final Review. This is video number 4. This will be our last video. We're reviewing Chapter 8 and Chapter 9. And you will need to have your quarter test review problems. And we're then going to do the 5 questions from Chapter 8 and the 3 questions from Chapter 9. You will need to have a periodic table ready to go. And you will, on the test, have this sheet of common polyatomic ions, the same sheet that you had on the Chapter 8 and Chapter 9 test. You'll have this on the final exam. But you don't have this in your possession, so you can refer to the first page of Chapter 9 notes. All right, the first question says, give the chemical formula for calcium phosphide and potassium sulfide. All right, calcium phosphide, and the second one is potassium sulfide. All right, well, first of all, let's just go ahead and write the elements down. For calcium, it's Ca. For phosphorus, it is P. And we need to look at the periodic table. So calcium is in column 2. It's a metal. It wants to lose the 2 valence electrons, okay? If it loses those 2 electrons, it becomes like argon, very stable, like a noble gas, and it would have a 2+ charge. Phosphorus is a nonmetal, so it wants to gain electrons. It wants to gain 1, 2, 3 electrons to be like argon. So it starts in column 5. It has 5 valence electrons, but it wants 3 more. 1, 2, 3. All right, so if it gains 3 electrons, it would have a 3- charge. So now we can take those superscripts, make them into subscripts. So it would be Ca3, and then that 2 that's above Ca would go here underneath phosphorus. So Ca3P2. All right, for the other one, potassium sulfide. So potassium is K. All right, sulfur is S. All right, let's find potassium. It's in column 1, has 1 valence electron. It's a metal, so it wants to lose that electron so it can become like argon. So if it loses a single electron, it would have a positive 1 charge. Sulfur's in column 6. It wants to gain 2 electrons to be like argon, so 1, 2. If it gains 2 electrons, it would have a 2- charge. 2 extra electrons would give it 2 extra negative charges. So then we could take that 2 and put it right here. That 1, we could move it over here, and we would have K2S. All right, so that's just the formulas for ionic compounds. You will definitely have to do some of that on the test. All right, so definitely work a few of those. Okay, so let's go on to number 2. Number 2 says, order the following atoms in terms of increasing ionization potential. So we have chlorine, tungsten, palladium, and phosphorus. All right, so remember with ionization potential, let's draw the periodic table like a rectangle. Ionization potential is the energy needed to take away an electron from an atom, and it increases as we go up and to the right. Okay, so we're going to order these. The instructions were to order them in terms of increasing. So lowest to highest. So of these four, the furthest to the left and down is tungsten. And then we would have palladium, and then we would have phosphorus, and then finally chlorine would have the highest ionization potential. So again, we would go tungsten, then palladium, then phosphorus, then chlorine. All right, let's look at number 3. 3 says, order the following atoms in terms of increasing electronegativity. All right, so we have cesium, silicon, rubidium, and carbon. Well, electronegativity is the energy with which an atom tries to gain another atom's electrons. Okay, and the periodic property is similar to ionization potential. You increase as you go up and to the right. So the least electronegativity, all right, let's look at the periodic table. Of these four is going to be cesium. It just has very little electronegativity. Next on the list would be just up one, rubidium. It has a little more electronegativity than cesium, but not much. And then we would scroll all the way across to silicon, all right, and then up one to carbon. Okay, so the way that you could write this out is cesium, then rubidium, then silicon, and then carbon. All right, pause the video if you need to, and we'll move on to number 4. All right, number 4 says, all right, order the following atoms in terms of increasing atomic radius. So we have rubidium, we have nitrogen, cobalt, and niobium. All right, so atomic radius is actually opposite the other two. If you think of the radius of a circle, and the smallest atoms are in the top right, and you get bigger as you go to the left and as you go down. Okay, so if we're ordering it smallest to largest in terms of increasing, okay, so the furthest one of these four would be nitrogen. Nitrogen would be the smallest of those. And then it looks like we would come to, let's see, where's niobium? Yes, then we'd come to cobalt, and then niobium, and then rubidium would be the biggest one. So nitrogen, then cobalt, then niobium, and then rubidium. So don't miss any of these on the final. There's not a whole lot to remember. Not many people miss these on the test, and it's a great way to pick up points. All right, so I'm going to erase this. Let's look at number 5. So number 5 has several parts. I want to draw the standard Lewis structure. That means I'm not drawing the shapes like we do in chapter 9. For Ca, we'll say CH3I. And then the second one is C2H6. And then the third one is ONCl. And the fourth one is CPBr. All right, so on this, we would have carbon is in column 4, so have your periodic table, and just as I talk, just look at the periodic table. Carbon is in column 4, so it's going to have, so let's, I'll go ahead and do this down, CH3I. So carbon's in column 4, so it has 1, 2, 3, 4 valence electrons. Hydrogen has 1 valence electron, and there's 3 of them. And then iodine has 7 valence electrons in column 7. Iodine can take a single bond, and hydrogen, each hydrogen can only take a single bond. It has, hydrogen is trying to get to be like helium, all right? It's trying to get 2 electrons. And then iodine is trying to go and be like xenon, so it just needs 1 electron. So each of those just has 1 open slot. Carbon's always in the center. So we'd have a single bond with each hydrogen. And then you would have a single bond, because iodine can only take a single bond. And then you have those electron pairs, those 3 electron pairs we need to draw. So carbon has 2, 4, 6, 8. That's what it wants. Iodine has 2, 4, 6, 8. We want the octet rule. And then hydrogen wants 2. So 2, 2, and 2 for each hydrogen. All right, remember, carbon is always in the center. I had some people not do that on the test. Okay, let's do B. So we have C2H6. All right, this time we have 2 carbons. We know that each one has 4, and each hydrogen, we have 6 hydrogens, and each hydrogen just has 1. So each hydrogen can just take a single bond. So the way this one would work out is we'll put our 2 carbons in the center. We would have a single bond with each hydrogen. Okay, it could be something like that. Now you couldn't put all, and then, excuse me, we've got another hydrogen there, another hydrogen there. And then what kind of bond would be between the 2 carbons so that each carbon has 8? All right, I'll let you think about that a second. All right, it'd be a single bond. So now each carbon has 2, 4, 6, 8, 2, 4, 6, 8. And each hydrogen has 2. It's really the only way that you could do this and get it to work out, okay, is to have, since hydrogen can only take a single bond, you couldn't put 4 hydrogens around one and 2 around the other, because then you wouldn't have any open slots. You wouldn't, the carbon that you only put 2 around would only have 4 electrons, okay? So the only way to meet the octet rule is to draw it like this. But you can always try a couple different ways and then erase as you go along until you get it right. Okay, C is ONCl. So we have oxygen, nitrogen, chlorine. Nitrogen's in column 5, so it's going to have 5 valence electrons. Oxygen's in column 6, so 6 valence electrons. Chlorine's in column 7, so 7 valence electrons. The one with the most unpaired electrons goes in the center, so that's nitrogen. Nitrogen has 1, 2, 3. Oxygen only has 2 unpaired electrons. Chlorine only has 1. Nitrogen would go in the center. What kind of bond can chlorine take? Well, it only has 1 open slot right here, so it can just take a single bond. What kind of bond can oxygen take? Well, it needs a double bond, right? It has 2 open slots. So we'll put oxygen over here. Don't forget those 2 electron pairs and the 3 electron pairs on the chlorine. Now nitrogen does have an electron pair right there. We need to draw that right there. And now oxygen has 2, 4, 6, 8. Nitrogen has 2, 4, 6, 8. And chlorine has 2, 4, 6, 8. All right, obviously you could draw the oxygen downward or draw the chlorine downward. Anyway, I drew it straight. We're not asked for the shape in this question. All right. And let's do D, CPBr. All right, we've drawn a carbon many times. Carbon's going to go in the center. Phosphorus is in column 5, so it has 5. And bromine is in column 7, so it has 7. All right, so let's put it all together. Let's draw those bonds. What kind of bond can phosphorus take? Well, it can take a triple bond, right? There's 3 open slots. So we'll put a carbon in the center and do a triple bond with phosphorus. And don't forget that electron pair that phosphorus has. What kind of bond can bromine take? Well, it has 1 opening, so it can just take a single bond. Let's draw it down here this time. That'd be fine. Draw those 3 electron pairs. We don't want to mess with those electron pairs. All right, phosphorus has 2, 4, 6, 8. Carbon has 2, 4, 6, 8. Bromine has 2, 4, 6, 8. All right, so if you want, you could draw that bromine up, draw the phosphorus up. Doesn't really matter. Don't have to do the shape. It didn't say do a shape, so you don't have to. All right. Let's move on to chapter 9. Okay, so chapter 9 says, number 1 says, give the chemical formula for calcium nitrite, magnesium phosphate, copper 1 acetate. All right, let's write these down. All right, number 1, A is calcium nitrate. B is magnesium phosphate. And then C is copper 1 acetate. All right, you're going to want to consult the table on page 1 of your chapter 9 notes. I am going to consult this. This is the sheet you will get on the final exam, and the periodic table, okay, to try to figure out these formulas. Well, calcium is in column 2 on the periodic table. So if it's in column 2, it has 2 valence electrons. It's a metal, so it wants to lose electrons. If it loses 2 to become like argon, if it loses 2 electrons, it would have a 2+ charge. Nitrate, all right, it's not nitrogen, it's nitrate. Let's find nitrate on the common polyatomic ions chart. It's NO3 minus. So now we're going to do the same thing. We're going to switch those superscripts and make them into subscripts. So that 2 will come down here. That 1 right there will come here. So we'd have Ca, and since we have more than 1 nitrate, be NO3 2. All right, magnesium phosphate. Magnesium, just like calcium, is in column 2. So it's going to have a 2+ charge. Phosphate is the very last one on your list, the only one with a 3- charge. PO4, 3-. So we're going to take that 3 and make it a subscript with magnesium. We're going to take that 2, make it a subscript with phosphate. So that's going to be Mg3 PO4. We're going to put that in parentheses because there's more than one of them. So Mg3 PO4 2. All right, copper 1, Cu is copper. It's a transition metal. That Roman numeral tells you its charge. All right, if it were 2, it'd be 2 plus. If it were 3, it'd be 3 plus. Acetate is on the sheet. All right, acetate is right here, C2H3O2 minus. Now they are both just 1. All right, so you can just write it like this. Since they're both the same number, if they were both just 2 or both just 3, it'd be the same thing. Cu C2H3O2. There's no need for parentheses because it's just one of these. All right, if they were both 2 and you were to put 2 and then a 2 here, I would have to count off. If they're the same charge, you have to get rid of those subscripts. All right, so having a sheet makes this really easy, so try not to miss any of these on the test. Let's look at number 2. All right, we have 5 of these. We have to draw the shape, give the bond angle. So PH2Cl2. We have SiO2. We have OCl2. Ci4. And SiCl2O. All right, this is a review, right? So PH2Cl2. So we've already done this multiple times. Phosphorus in column 5. Hydrogen in column 1. Each chlorine in column 7, so it has 7. So each hydrogen, each of the 2 can take a single bond, and so can chlorine. So we have 1, 2, 3, 4. All right, if you want to draw the second hydrogen and the second chlorine, each one of those can only take a single bond. So if you have in the center, the central atom, phosphorus, surrounded by 4 single bonds, that's a tetrahedron. All right. Okay, so we're going to draw phosphorus in the center. Just go ahead and put chlorine like this. Oh, excuse me, that's a hydrogen. Don't forget the electrons. So it's tetrahedron. (109° bond angle. You just have to memorize that. All right, don't forget about the fat line. And then now let's go ahead and answer number 3. Okay, number 3 says determine. Well, no, we'll go ahead and do it. Is this purely or polar? Well, because chlorine and hydrogen are different, it actually is polar, so it will dissolve in water. The question didn't ask that, but you'll have to answer potentially that on the test, so it's polar. Let's do SiO2. All right, silicon is in column 4. Each oxygen is in column 6, so it has 6 valence electrons. We have 2 of them, 2 oxygens. So we're going to put silicon in the center. Each oxygen can take a double bond. It has 2 open slots. So when you have a situation like that, in order for the electrons to get as far apart as possible, it will assume a linear shape. Remember, the electrons are trying to get as far apart as possible. So a linear shape is a 180° bond angle. All right, so if we want to draw the arrows here, we have an even tug of war, right? This molecule, the oxygens have the same electronegativity, an even tug of war. So this one would actually be purely covalent and would not dissolve in water. All right, I realize the question didn't ask that. I just thought I'd throw that in. All right, let's do OCl2. Okay, oxygen, column 6, each chlorine in column 7. Chlorine can only take a single bond. All right, if I have a central atom, one oxygen, surrounded by 2 single bonds, it's a bench shape. Okay, central atom, that's oxygen, 2 single bonds. All right, so to draw this, we put oxygen in the center. Don't forget those 2 electron pairs. We need to draw those. Don't forget the electron pairs around chlorine. It's a bench shape. And the bond angle is 105 degrees. Just got to remember that. Bent is always, so it doesn't matter which one wins the electronegativity battle. Oxygen does in this case. Bent is always polar. So it will always dissolve in water. All right, let's take a look at Ci4. I realized that I actually, what was listed on the paper was PHCl2. So I'm going to draw that as a 6th one in a minute. I did draw this one correctly as tetrahedron, but I want to draw PHCl2. So hold on with me if you notice that I wrote that down wrong. We'll fix that in a minute. All right, Ci4. So each carbon in column 4, which is just 1, and then iodine has 7. So we have 4 single bonds surrounding a central atom. Again, tetrahedron. All right, so that'd be iodine. Don't forget the fat one there. Now this one's different than the other tetrahedron because all of the atoms surrounding the central atom are the same. So yes, it's tetrahedron. Yes, it has a bond angle of 109 degrees. But this one, since all of those poles from the iodine cancel, it's purely covalent, so it would not dissolve in water. Okay, let's do a couple of more. SiCl2O. Silicons in the 4th column, 4 valence electrons. Each chlorine has 7, and each oxygen has 6. Those 2 chlorines both have a single open slot, so they can take single bonds. So we have 2 single bonds, but the oxygen can take a double bond. If you have a central atom surrounded by 2 single bonds, 1 double bond, it's trigonal. All right, so let's draw it like that. Silicon in the center. So the name is trigonal. Don't forget to write down the name. Bond angle is 120 degrees. That bond angle is how far can these guys get away from each other? All right, 120. A circle is 360, so 120 is the best it can do. Trigonal is always polar because you have different atoms, so different pulls. All right, let's do F, because I wrote this down wrong and I don't want to redo this whole video. So I wrote it down as PH2Cl2, which is a valid compound. We're going to do PHCl2. Okay, because that's actually what A said it was going to be. So PHCl2. Phosphorus, column 5, 1 hydrogen in column 1, and each of the 2 chlorines in column 7. So I've got a central atom phosphorus surrounded by 3 single bonds. The hydrogen can just take 1 and the 2 chlorines can just take 1. A central atom surrounded by 3 single bonds is the pyramidal shape. Central atom, 3 single bonds. All right, so that's going to be, we'll put the H there. Doesn't really matter what you put where. Just make sure you get that fat line and that dash line. So this is pyramidal. Bond angle is 107 degrees. And pyramidal is always polar. All right, because you're going to end up having, you're always going to have movement, because the central atom will have a different electronegativity than the surrounding atom. So we'll have either a downward pull or an upward pull. All right, that does it for number 2. Number 3, we can answer those really quickly. Number 3 says we want to determine if the following are polar or purely. So SiO2, OF2, and HBr. Now, I'm not going to go through the long explanation of how to draw these. All right, so SiO2, we drew this before, and it was linear. So you have an even tug, even electronegativity tug. It cancels out. The tug of war there cancels out. So it's going to be purely. This molecule wouldn't move, so it'd be purely. So does not dissolve in H2O. OF2, if you were to draw this out, go through the process, it would end up being bent. All right, so if you're not sure why, go through the process, draw this out. Fluorine wins the electronegativity battle, and this molecule is going to be pulled downwards by that fluorine, so it's polar. So it dissolves in water. HBr. All right, that's just H has a single electron. Bromine is in column 7, so that's just you can just have a single bond there. So it's like this. So it's a linear shape, but bromine wins the electronegativity battle. And it doesn't really matter which one does. They're different. So since this molecule is going to move, it doesn't cancel out. It would be polar. All right, so it dissolves in H2O. So my suggestion, since we just had chapter 8 and 9 test, if you did well on the test, maybe this is good enough for you. If you didn't do that well on the test, now our final has no vocab on it. It has no matching. It may have some multiple choice and true false, but it would be multiple choice and true false related to these kinds of questions, not to vocabulary types of questions. So the suggested additional chapter 8 problems, just extra practice problems 2 through 10. That would do it enough. Remember, you have the sheet that has all the answers. And then suggested additional practice problems from Chapter 9 are just the extra practice problems 1 through 7. Rework those, and you should be good to go on the final exam. So that is all that I have for video review for this final exam, the second half of Chapter 5 through Chapter 9. This counts as 1/2 of your final exam grade. It will be averaged. It's going to be averaged with the first quarter test that you took back in late September, early October. Okay, so average with the first quarter test. Average the two, that goes in as your final exam grade. Your final exam is 20% of your semester grade. So ultimately, this test that you're going to take, 5B through 9, is just 10% of semester grade. So it can move your grade some without question, but 90% of your grade has already been earned. And good luck, study hard. Let me know if you have any questions.